Welcome to Burcu's Take on Week 2. This week, we learned about limits and continuity. Unit 2 started with the concept of limit. First, we reviewed the formal definition of limit from Calculus 1. In Calculus 1, we've seen the epsilon delta definition of limit. Our definition of limit for functions with two variables is a very similar one. But first, note that for the one variable case, we can only approach the limit from two directions, from the left and from the right. To be able to say that the limit exists, limits from the left must agree with the limit from the right. For functions with one variable, we said if x is really close to a, then f of x is really close to L. For functions with two variables, we'll say if the point xy is really close to the point x0, y0, then f of xy is really close to the limit value L. In the plane, there are infinite directions from which xy might approach to a point AB. You can approach from left, you can approach from right. You can approach in the direction of northeast or in the direction of northwest. Actually, we don't have to restrict ourselves to a particular direction. We can even approach to that point along a path that is not a straight line. Back to the formal definition. In Unit 2, we also introduced the formal definition of limit for functions of two variables. We also studied some limit theorems that made our limit calculations a lot easier. When studying the limit of a multivariable function, it is possible to arrive at different limiting values by approaching to the point of interest along different paths. If this happens, we say that the limit does not exist. In this example, we're going to look at the limit at the point 0, 0. Approaching along the straight lines going through the origin, we see that the limiting value is 0. But if we are approaching to 0, 0 along the curve y equals x squared, the height of the corresponding point on the graph of this function is 1/2. Since the limits do not agree, we say the limit does not exist. This is analogous to the left and right-hand limits of single variable functions not being equal. But what goes wrong in the limit definition when two different paths give two different limit values? This definition tells us that the distance between f of xy and L can be made arbitrarily small by making the distance from xy to AB sufficiently small but 0. But it only refers to the distance from xy to AB. It does not refer to the direction of approach. So if the limit exists, f must approach to the same limit no matter how xy approaches to AB. Therefore, if we can find two different paths of approach along which the function has different limits, then it follows the limit does not exist. Proving that the limit exists is a little more work. It involves working with absolute values and inequalities. First, you need to try approaching a few different paths to find a candidate limit, and then use the squeeze theorem. You can also use the epsilon delta definition. We just did not go into the details of this in this course. Before we jump into the continuity definition, I wonder how one can define the limit of a function with three variables. Will the definition neighborhood be sufficient, or will we need a new definition? Just something to think about. Recall that in Calculus 1, there were three requirements in the definition. F of a must be defined, left and right limits must exist, and the limit must equal to f of a. In brief, we meant that the graph of a function did not have any breaks, holes, jumps, etc. We define continuity for functions of two variables in a very similar way. We say that a function f of xy is continuous at a point AB if and only if the limit of f as xy approaches to AB equals f of AB. Just like in single variable calculus, this corresponds to three requirements. F of AB must be defined, the limit must exist, and be equal to f of AB. So what's coming up next week? Next week we will take baby steps to differentiability. Since we have several variables, naturally we take derivative with respect to each variable separately. We will call each a partial derivative. Before we formally define differentiability, we will first take a look at the geometric interpretations of the partial derivatives and use these interpretations to study linear approximations. We hope you find these videos helpful to wrap up the week. Have a nice weekend.